of this collaboration, and many of you I think I see first time, and I'm really looking forward to learning some exciting things. I'm not an expert on FluxCube, and I will be talking about some work in progress with my student Elizabeth Armanini and Kenan Herring, and some of the paper, which I thought suits this workshop. But if I say some nonsense, please forgive me. So, and I think the idea would be that I thought that this topic is interesting because it's related to many papers recently in last couple of years, and that appeared which somewhat do not talk to each other, but I will try to put them together and discuss in some framework. And yeah, and the idea would be I will talk about the dynamics of flux tube as usual, I guess, at this workshop. I'll start with the usual picture, but the idea is that I will simplify my life and consider it to be conformal. So I'll consider conformal gauge theories. At large n, and we will be interested in dynamics of flux tube. So, well, the first thing that happens, of course, is that if you have a quark and anti-quark, and Gabriel drew this picture yesterday, if you don't have confinement, so the flux line, they just go all the way, and go all the way to infinity. And if you if you look at what is the potential, because it's a conformal gauge theory, the potential is fixed by dimensional analysis to be like this, 1 over L. So it's just a Coulomb potential between the charges, but if you take the large n limit, the string is still well defined, it doesn't break, so it makes sense to discuss the physics of the string. Now, this vacuum energy, this potential energy, it can depend on the coupling. And to simplify my life, I will assume not only that coupling is, that the theory is conformal, but I will also throw in some supersymmetry, and let's imagine it's n equal 4. Some of the things will simplify in this case. And we want to understand dynamics, again, according to the usual laws. There should be string descriptions that emerge in this limit. Well, and it does, famously, and the picture is like this. You now imagine this thing being drawn on a plane. Sorry. And there is a radial direction. So this thing is on the plane in radial direction. And this is ADS. And the string that emerges will take this shape. And it's nothing but a fundamental string, which lives now in ADS 5, say, cross S5. You can compute this, and then you can study, of course, like Gabriel discussed yesterday, the spectrum of the string. And we believe that it's integrable. Well, it's an integrability of n equal 4 super Yang-Mills. But if you consider scattering of such strings, then it's an interesting problem. And I will be eventually interested in scattering of such strings, so open strings, in the conformal gauge theory at large n, so it will be the physics of this flux tube. Now, if you compute this thing at, at weak coupling, it's just something like lambda pi. If you compute it at strong coupling, it's related to the tension squared lambda. And based on this picture, you would think that the physics, there is no lambda QCD, there is no dimensional full scale, so it seems like it's a bit of a boring thing. Nothing happens as you go from weak to strong coupling. But there is this really, really beautiful paper by Igor Klebanov, Juan Maldacen, and actually Charles Thorne, maybe, from 06, which I recommend. which pointed out that dynamics of the string is very different at weak coupling and at strong coupling.
That was for the joint.
Sorry?
That's what they were discussing lines in the joint, right? In the
I think they were discussing lines in singlet. Yes. Because for the joint, a joint lives in the continuum, and the singlet has a set of the ground state and then the set of perturbations. The picture, what they pointed out is that there is this, the picture is very different, and as we discussed a bit yesterday, that if you have the string, you can start, you can start perturbing it, you just shake it a bit, and there is some set of modes. And so, in fact, with strong coupling, what you expect is that you have you draw energy, so there is a ground state here, and it's under L, and then you have a continuum of states, and this continuum of states related to the fact that in principle you can consider a string. You can consider a string which goes all the way to the horizon, to the ADS horizon, and this string has a finite energy. And the reason it has finite energy, you would think that, well, how come it's an infinite string? And the reason is that in ADS, as you know very well, this direction has a redshift factor. And so if you compute the energy of the string, it has this redshift factor d over z squared. And so if this is 0 and this is infinity, this is a finite integral, so it has a finite energy, and so then you can have this strings going apart, and so this corresponds to the continuum. But you have a set of infinitely many, in fact, bound states. And and this is very different from weak coupling, which they also analyzed. And in weak coupling, you have this bound state, so lambda strong, lambda weak. You have the same continuum, then you have a single ground state, just this. And then there is a transition at finite coupling, where suddenly all these bound states appear. And so let me make 3 points from that paper.
Just to be sure, I'm studying the spectrum with 2 Wilson lines in such a finite separation.
Yeah. Yes.
It's not the connected Wilson line for the Wilson loop.
It's you can think of this as a just rectangular Wilson loop in a large TLMF. And so then you have this Wilson loop being e to the minus t times set of energy states as a function of L, where the set of energy states are all of this type, and we are studying the spectrum.
Sorry, is there any Euclidean counterpart of this state? Because it's horizon. Like if I had just Euclidean ADS, I won't have any horizons. So this continuum, I just don't see it. Or? What you just said was some Euclidean, e to the minus ETL.
Yes.
But I do not see it in Euclidean.
I don't know what to say, but let me let me say what I thought I hope.
And maybe one question. What do the bound states, is there a picture associated to the bound states?
Yes, that's what I will say now.
I have one last question about the first. So the first potential piece, I should think of this roughly just as the potential energy of the string. Like
It's just the energy of the string, and
what about the infinite length? I mean,
yes. So this you subtract. You just renormalize this infinite length.
and then that's just some divergence in the
Yeah.
Gibbs theory of like a self energy or something. Okay, thanks.
So the interesting thing here is that what they pointed out in that paper is that you have a transition which happens at finite coupling, and they model this transition by some. They pointed out that you can model this transition by considering resumming some set of later diagrams, which effectively leads to a Schrödinger equation of this type. This is not controlled approximation, but it's a toy model for this thing. They pointed out that you can have this, if you consider the Schrödinger equation, you consider a set of bound states, you find that when lambda is less than, this lambda is coupling, when lambda is less than 1/4, you have a single ground state, and when you have this lambda larger than 1/4, then you have infinitely many, and the idea is that this is related to fluffiness of a string. So when at weak coupling, the string is very fluffy and you cannot really, it does not support vibrations, but here it starts supporting many vibrations. And so this is one point. Well, the second point is that these strings compared to the...
What is behind this equation?
So effectively, I guess it's a effective Schrödinger equation which captures the spectrum of the string.
Okay.
Yeah. Again, as I said, I'm sure there. Okay. Now the second point, which I guess here and which is different compared to confinement. Confining string is that there is this ionization threshold, where you have a continuous spectrum, and the bulk it corresponds to the fact that you have an ADS horizon. And when you have a confining background, then you know that the geometry is capped off at some finite ADS, and these states disappear, and you have discrete spectrum all the way. So that's one difference. And the third point, which was very interesting that they made, is that the spectrum of the string, only strong coupling, has an accumulation point. The accumulation point is related to the following solution. You can consider, if you take a string, which is, you can start excited in a radial direction. In particular, you can imagine stretching a string such that it goes to, let's say, I put some horizon, z equals infinity. So you put the string very, very far, so effectively it looks like a folded string, and then you let it go, and it just is pulled back by the radial potential, and the tip moves in the close to the boundary. This type of solution, what happens is that, well, you start with some energy of the string, which is dv over z square, which goes up to some z maximum here. So it's proportional to -1 over Zm. And then, as you let the string go, it's pulled, so it quickly becomes just moving with the speed of light. So it becomes like a massless particle pulled by a string. And if you write the momentum conservation, so this momentum, which or energy of a string, plus the string which is left as the particle moved, which is something like 1 over z, minus 1 over z should be equal to this energy, which is minus 1 over zm. And then they say we can take this classical solution and do a semi-classical quantization, which is something like n, which is much larger than 1, is equal to 2 pi pz dz. And you got Bohr-Sommerfeld quantization of such strings, and so you see here you get integral dz over z, and so effectively you get a set of states where here you get log of this maximal position, zm, so you get log minus e, and so the prediction is that this strings has an accumulation point which behaves like this. So the prediction is that there is this interesting feature that emerges, which is that you can consider now the string going all the way to the horizon, and there are these solutions which correspond to accumulation of energy eigenstates close to the ionization threshold. So this is the point that they make. And you can, in fact, this problem, as I said, it was because the flux tube in N=4 is integrable. It was analyzed for this potential using integrability methods by Gromov and Levkovich-Masluk in 16. So they found this function can be computed using the quantum spectral curve, but to the best of my knowledge, these states have not been, the spectrum has not been worked out using integrability, but if one of you know, please correct me. So it seems like this is a solvable problem, but hasn't been solved. But here,
the idea is that this accumulation is for any coupling bigger than 1/4 or only for infinite coupling?
1/4 was a toy model thing, but yes, the idea is that there is if you take this toy model, there is an accumulation point for any lambda larger than 1/4 here. So somehow the prediction is that as soon as you go through this transition, you have this infinite number of states, and then you have this accumulation point, but I don't think it has been shown using integrability. That's my understanding. But the physical picture is this, and then you can ask, can we see these states in the confining gauge theory? And I guess the picture is the following: that you have a potential which is the sum of a Coulomb potential plus a confining potential. This is the physics of the Coulomb potential, and if you have enough radial direction, if your string is stiff enough, you should start seeing these vibration modes. In actual QCD, we do not see them, so the string is fluffy, and we do not seem to be seeing these states. That's an interpretation, but presumably, if you take a confining gauge theory where the UV fixed point is strongly coupled, the spectrum of the string you would expect it will transition between, say, maybe some of these modes, which know about the radial direction, and then it switched to the confining, where the horizon is cut. That's
Is it UV coupling that matters, so more like at which coupling you confine? Suppose QCD was kind of first, was confining later, that it was reaching some fixed point with strong enough coupling, because this doesn't it matter what happens close to the horizon rather than what happens close to the boundary?
Good question. Yeah, I think. I don't know.
Is there a sharper intuition for the bound states than the fuzzy string? Because in the weak coupling regime, I would have thought that the massive modes are easier to access for the string.
One intuition why these guys, these guys disappear, that they offer, again, I apologize if it's already obsolete, but the intuition that they offer in that paper is that as you reduce the coupling, somehow you should start thinking of this tip as developing a mass, like in yesterday's talk. And then there are two effects where there is a pull of the string and there is a gravitational pull towards the horizon. And the pull of the string, as you reduce the tension, decreases. And so the thing just falls and you do not have such bound states. That's the intuition that they suggest. So the intuition would be that as the string becomes more tensionless, this pull becomes weaker, but and it eventually cannot support the gravitational pull of these things, and so they all fall into the horizon. But that seems like a nice picture that they offered, and I guess in principle it should be possible to just check all the statements and do it fully. So these are the three lessons I wanted to bring from the papers. That if you go to the conformal gauge theory at strong coupling, you expect the ionization threshold, which corresponds to the horizon in ADS. You have a trivial potential, but the set of bound states depend on the coupling. And the third is that at strong coupling, you have this accumulation point for the strings. That's 3 points I wanted to make from this paper.
What is the physical meaning of these bounded states from the
We will come to that next. Yeah. So I will. Now this was 2006, and now I will move to 2022, which is there is this paper by Maldacen and Bremen, which is called Accumulation Point Amplitudes in String Theory. Now, what did they? This is a little bit to put it in the context. People have been studying doing asymmetric bootstrap, and I guess there will be some talks. And they were finding that sometimes you find these amplitudes with accumulation points where there are infinitely many states at some given energy, and they seem unphysical. And in the point of this paper was that they wanted to point out that there is a setup which realizes this accumulation point. And the setup was similar to that, slightly the following. You consider now boundary, horizon, so this is equals 0. And then you can consider some say D3 brane here, somewhere in the bulk. So we can put it z equals 0 equals to 1. And I will discuss, of course, what it means. Then in the gauge theory, so you can consider now open strings here. And you can consider scattering of open strings on this D3 brane. There is a parameter in this problem, so notice it's the ADS does not really have ADS does not really have a scale, so the actual parameter you have here is alpha prime over r ADS square. That's a dimensionless number, and you can take it whatever you want. So let me measure everything in the units of r ADS. And they make the following point. So let's consider this scattering amplitudes for the strings, so open strings on the brane. And there is an amplitude, which we call A, gamma, S, and T, which has the following property. So first, you expect that this amplitude. When you can form, in the collision, you can form various strings, and in particular, you can start forming this kind of strings that stretch to the horizon, and then go all the way to the horizon. And the interpretation that this amplitude has a continuum of states at alpha prime s for 1 over gamma. So this is simply I think this is simply a mapping of this calculation. I set everything here to 1, alpha prime RADS, but if you restore, you get this relation. And notice in the language of gauge theory, this guy is 1 over square root lambda. This is a 't Hooft coupling. So when the 't Hooft coupling becomes big, the continuum is very far. The continuum of states. The second property of this thing is that they say it has an accumulation point. And this accumulation point, they suggest, is just because of these states, in this intermediate states. If you look at radio trajectories, this is related to spinning strings. You can consider a brain in ADS, and you can consider a rotating string. Just a rotating string which rotates on the brain. It's a classical solution, and you can find the radio trajectory. And what we find is that well, it's large, but not too large. Not too large spin. It's linear. So this is the intuition simply that let me take the ADS radius much larger than the string scale, so lambda to be very, very big. Then effectively this rotating string is just a flat space string, and this is the usual linear radio trajectories that we all know. However, if you consider the states which, if you start spinning it faster and faster, it will start sensing the ADS radius, and the radio trajectory becomes as follows. It approaches the accumulation point with this number which is computable, 1 over j squared. So basically, you have so notice that this accumulation point is for strings which are not spinning. It's just j equals 0 effectively, but this is really a spinning string which has the following spectrum in ADS. So it's a radio trajectory which is straight, and then it's bends up at accumulation point. Another property of this amplitude is that at low energy it becomes Veneziano. So if you take alpha prime s gamma to be much less than 1. So this is again something you can do at strong coupling. This is a very small number. This can be even big. And this is probably small. Then this amplitude becomes, say, Veneziano. At high energies, it becomes Aldheim-Aldassem. So if you take the log of this amplitude, it looks like this. which corresponds to now a minimal surface in the bulk, and this happens for alpha prime as gamma much larger than 1. So effectively, this also corresponds to the, I guess, the Regge trajectory at large negative. So this is a, as you remember, spectrum of Regge trajectory for positive spin corresponds to spectrum, and this and the negative t for negative energy square corresponds to scattering. So this Venezian amplitude has a straight leading linear Regge trajectory, which is the same as this. But then at large negative t, it bends and becomes.
Sorry. Could you draw some Regge trajectories? Is that possible to
Yeah.
visualize?
Goes up. Star. And this here should flatten out.
That's the leading one, and
It's the leading one, yeah, and
they all blow up at the same point.
yeah. That's the idea. And again, that's has to be studied, really, but that's what people do.
And then there's a cut after, so it blows up and turns into a cut.
Exactly. So there's a cut here, there's a blow up here, and this blow up is approached like this. So it's 1 over square root t star minus t.
And this limit is S and T.
So both large. Fixed angle. That's fixed angle.
Fixed angle.
Their paper was the point of their paper was that they say, well, that's what you expect, and this is a completely healthy behavior. And in fact, there is a paper there is an amplitude which was discussed in the literature in the last few years, so-called Kuhn amplitude, which is an explicit. I don't want to write it, but it's an explicit formula you can find in their paper, and it's a deformation of Veneziano amplitude. And they pointed out that if you look at the Kuhn amplitude, it has the following properties. It has a continuum of states at some point. Then it has accumulation point. It looks like Veneziano at low energies. It looks like Aldaimel Dasen at high energies. So they say, well, it looks like some screen scattering and maybe possibly some background, but there are two differences. First, this is also true. First thing that doesn't hold is this, because in the Kuhn amplitude, the Regge trajectory looks like this: 1 minus e to the minus j. So it's not quadratic. It approaches it exponentially. So effectively, in the Kuhn amplitude, you can just take this formula and set n equals to j. And this will be the right leading Regge trajectory. So this is different. And the second thing which they didn't know yet at the time, when they wrote the paper, but which was pointed out by Christoph Jepsen in 23. Which is that you can consider unitarity above the cut. And even though, yes, and here, of course, here you have a bunch of bound states, and you can check unitarity on the poles. So you know you have an amplitude, you look at the residue, and it has to be positive definite, and Kuhn amplitude satisfies that. But what was pointed in 23 by Jepsen is that if you check unitarity above the cut, the Kuhn amplitude is not unitary. So the status of the story is that Coulomb amplitude, whatever it is, it cannot be something in a consistent string theory, so something extra ingredient is needed above the cut to make it unitary, and it also does not look like a scattering. The Roger trajectory is very different from EDS horizon, which has this very specific prediction.
But the original Coulomb amplitude is unitary, it just doesn't have the infinite number of particles, right?
Sorry?
The original Coulomb amplitude, not the modification of Christian and others, is unitary, right? But it doesn't have the cut, it just has this infinite number of particles.
No, I think it's well, the Coulomb amplitude, it has accumulation point and has cut above, it has a cut after accumulation point. And on the poles, it is unitary. But then you can consider it above the cut, decompose it in partial waves, and the imaginary part should be positive.
But there are, I'm asking, but there are several modifications of the Coulomb amplitude, because I think the original one had infinitely many particles at each level. That sounds like. So I thought that.
Why do you say it just has this rigid trajectory? You go to each point, it has finite number.
If you try to decompose, I think, the residues of the poles in Lejeune polynomials, you find that you need infinitely many Lejeune polynomials. In the original Coulomb amplitude, I thought the people considered modification, and those modifications were C. Maybe
I think, well, we can discuss, but I think the original Coulomb amplitude has a finite number of particles. It does not have, if you look at the poles, it's just perfectly sane.
Okay.
So, my understanding that the current status of the Coulomb amplitude is that you can consider ones which maybe do not have accumulation point and then they are non-unitary. You can consider one which accumulation points are unitary on the poles, and then they are non-unitary above the cut. So that's the current status. And yes, the conclusion of this paper, the end punchline was that Coulomb amplitude might correspond to strings in some suitable background. But okay, this point makes it clear that we need to add something. But now I want to say, okay, well, seems like this scattering on these brains, it seems like a very nice object to study. It has all these remarkable properties. So what does it correspond to in n equal 4? And what do we know about this amplitude? Then I will want to discuss a little bit. Okay, so what are the accumulation point amplitudes in string theory? Somehow here, I just commented on the connection to this Coulomb amplitude, but what about the actual amplitude? So that's what.
Can this open string pinch off and sort of fall into the horizon at high enough energy?
Yeah, I think at high enough energies, it cannot. The emission of closed string is as usual 1 over n suppressed, but the continuum of states corresponds to the strings stretching all the way to the horizon and coming free. That's.
But you don't see this in any studies of unitarity. It's not an issue.
Well, it's. No, I think it's a totally legitimate amplitude. Somehow in Bootstrap, maybe we haven't looked at such amplitudes because of accumulation points. Maybe. But in fact, what I will say is that there is a huge literature on this amplitudes. So that's what I will explain next. But the basic, here, what I want to say is that it seems like there was this amplitude that doesn't quite work, but maybe a good target for the flux tube is let's first solve this flux tube. Because it's very rich, and it has integrability for the spectrum. And so now I would like to discuss, well, can we solve this? Can we solve for this amplitude? That's what I want to review next. And the question I would like to pose, and it seems to me that this is a wonderful target, but it hasn't been done yet, and it seems to me that some conceptual points are missing. Okay. The settings that I will consider is planar n equals 4, and then because we're having this brain in n equals 4, this corresponds to going on a Coulomb branch. So we give a VEF to one of the scalars, and then the theory at low energies flows to SU n minus 1 times a U1 supermultiplet living on this brane, and we can consider scattering of these particles on this brane, and this corresponds to the problem. So that's the problem we want to analyze. It's an n equal 4 and a full branch. And this, of course, has been studied a lot. And I would like to review what we know and to connect to some of the stories, which has not been really done. And the first paper, which I think did it, observed something really nice also about these amplitudes, was by Aldai, Hen, Plevke, and Schuster in 2009. And what these guys did is they say, well, let's consider this picture again. You have a boundary, you have a horizon, and let's say you take 4 of the branes. So you give 4 different VEFs, and now in principle you have so they have some coordinate in the AES, and this is on the boundary related to the mass of the W bosons, of the mass of this guy going from here to the horizon. But you can consider scattering of open strings like this. So guys like this. And if you consider this scattering in ADS, what you see is that you can perform T-duality on these branes, and you get in the T-dual picture Wilson loop. And because it's a Wilson loop in ADS, they see that you expect to have, it's a standard again argument, you expect to have a dual conformal invariance. This is their observation, and then they say, well, do we expect this dual conformal invariance to survive with coupling? And to analyze this, they say, well, let's consider this object at weak coupling. And at weak coupling, what they did, well, they set up the strings and to leading order, the non-trivial diagram turns out all the bubbles and triangles effectively cancel. So you just consider this box diagram where the propagators, so it's just a set of propagators that are massive, and this corresponds to W boson, string stretched between this probe branes and the horizon. And the external guys, they're massive M1 minus M2, M2 minus M3, M3 minus M4, M4 minus M1 squared. It's all squares, so it's all positive. And you can compute this amplitude. Of course, it's one loop. And what you find is that it's a tree level. The prediction of dual conformal invariance, which effectively what is kind of amazing about that is that a priori you have momenta, which is a scattering momenta, and the masses. But in this picture, they all unified masses and momenta into single 5-dimensional geometry. And in practice, it means you can show that this dual conformal invariance implies that the amplitude should take the form of a tree level times a function of 2 cross ratios, M4, U, and V. Where the cross ratios are M1 minus M3 squared minus S, and V, M2. Well, and surprise, surprise, you do the one-loop computation and you find that it's correct. So there is this amazing property of dual conformal invariance for the amplitudes, which implies this thing. And notice that here, however, if I put all these 4 branes on top of each other, it equivalently makes these particles massless and all masses to be the same. And then this statement becomes somewhat trivial because U is just m squared over s, T is m squared over T, so it's just dimensional analysis. So this becomes somewhat trivial, and maybe you will not be so impressed by that. But then something interesting happens, and let me also point out some, maybe an obvious fact, but I find it kind of remarkable. So here we are dealing with the object A gamma, and the statement is that at weak coupling it's a one-loop box, and at strong coupling it's a Veneziano amplitude. And so these two are continuously connected. So Feynman one-loop box and Veneziano amplitudes are describing the same dynamics of the string. One is a weakly coupled dynamics, one is a strongly coupled dynamics. And you see, the picture, however, is completely different. Here, if you take this box, it has a cut at 4n squared. Right? It has a cut and nothing else, no bound states. Whereas if you look at Veneziano amplitude, it has only bound states and no cut. So what is happening? Well, what's happening is that as you turn on the coupling, this guy develops bound states, and as you take coupling to infinity, the cut goes infinitely far, and you see only bound states. And vice versa. As you reduce the coupling, this guy develops a cut, and then as you reduce coupling more, the bound states go away, and you go this. But it's an object which combines these two very familiar things.
So here is it all masses of like external and internal states, they're related in some simple way because they all come from Higgs.
Exactly. They all come from Higgs, and so they're all related. And so then you can ask, okay, where are the bound states? Why don't we see the bound states? And here comes the next step in this story. And this is the paper from 2015 by Simon Caron-Néot and Johannes Hahn. So what about the bound states? One thing which you remember is that you could ask, okay, well, we have n equal 4 super Young-Mills, it's a CFT, okay, it flows, but this object has infrared divergences in principle. The nice point here is that all the infrared divergences are 1 over n suppressed. So to leading order, it's really a well-defined object, there is no question, and you do not see any IR divergences. However, if you take one of the masses to 0, so you move back the brane, then you will start seeing the IR divergences, they will reappear, even to leading order. So therefore, you will expect that when you take one of the n's to 0, it's controlled by universal IR physics of the divergences of the scattering amplitudes. And what they pointed out is that, in that paper, is that if you take u to 0, the cross ratio going to 0, you can do it in two ways, looking at this formula. First, maybe let me do so follow v goes to 0. You can do it in two ways. First, you can take t to infinity, and this corresponds to the Regel limit. Or you can take m1 to 0, which is a soft limit. And these are things to dual conformal invariants. They're the same. So they should be controlled by the same quantity. And from this, they predicted that if you consider this m function, let me remove 4. if you consider a radial limit. And now, by the way, after you realize that, you can then set all m's to be equal again. The prediction survives. You can take then all the m's to be back equal, but the prediction becomes that the radial limit of this object, a gamma, which is up to 3 levels the same as this m, is given now by 4m squared minus s, 4m squared minus t. Here, it's the same thing. I just set all the masses to be equal. Cancels. It becomes s to the trajectory. And the prediction is that J0 of t plus 1 is equal to minus gamma cusp of phi. So it's a cusp anomalous dimensions of the loop, which controls the IR behavior of the amplitude with t related to phi as 4m squared sine squared phi over 2. And again, there is it's a beautiful physics, and I'm still need to understand everything that's happening. But basic conclusion is that we have this relationship, and of course now what we see here. These are all very general properties about strings and in ADS, following from the horizon, from flat space. But now there is a prediction for the leading radial trajectory, which generalizes the usual statement G of T Veneziano to any coupling and to any T, because the gamma cusp is known from integrability. So the statement is now we know that this thing, we know the leading radial trajectory of this amplitude, and now you can consider, well, as you know, the bound states corresponds to J0 of t equals to integer. And if you plug this here, you find this rotating string radial trajectory that we discussed. So this is what they called in the paper hydrogen atom. This is just a statement that you recover this accumulation point. And the accumulation point here in this picture is simply 4m squared. So 4m squared is the location of this horizon, if you wish, in this.
Is it related to the initial picture because the small angle cusp is just the potential?
Yeah. So somehow when you have to take phi to pi. When phi becomes pi, it's like two strings on a sphere very close, and that's related to the potential. Yes.
And the internal angle here is the same for the two Wilson lines, or it's not specific in this case?
I think it's the same. It's just the internal angle is 0. Again, I think it can be all generalized to a general angle, etc. So now.
Sorry, Sasha, this is a bit somehow I'm confused. So that was just some one loop calculation, and then you somehow hear what happened, the intuition behind this formula or range of validity.
So now you do the finite coupling computation, and you say that at finite coupling the IR divergences are universal, and so you can take m to 0, and you will get m to the gamma cusp. That's just a universal prediction. Yeah. But now you say that, well, the same thing happens as t to infinity due to dual conformal invariance. Therefore, you get just, basically, you just get t to the gamma cusp.
The first assumption is that you say that dual conformal invariance works to all loops, which is kind of okay because it's strong coupling, it works, weak coupling works, so you say it always works.
It always works, yeah. And then you use this picture of infrared divergence related to gamma cusp.
And then, so here you say z is 1 over m. In that picture you said z to 1.
Yeah, z, here there is conformal invariance, you can set it to whatever you want. Really, the only parameters are alpha prime s and alpha prime r ADS. So everything depends only on these combinations and z naught. It's really, you can
accumulation. So here accumulation point was set by the coupling, right?
Yeah, here accumulation point was set by r square alpha prime. And what happens, which is 1 over square root lambda. And what happens is the following, that as we charge the coupling, this potential was going down. What happens here is that you develop these bound states and they start going down and they start approaching 0. So they appear, they're a little bit below 4n squared, and then you increase the couplings, they start approaching 0, and they approach 0 as 4n squared square root lambda. So now if you say this is my new gap, you rescale this thing which was fixed by the VF of your field, then your cut goes very far. But the picture is that, you start, basically think of, you can set m to 1. Again, that's Higgsing does not play any role. You can set it to 1. Everything just depends on the ratio s over 4n squared. So the fact that you can set m to 1, it's the same as you can set it to 1. Everything just... Exactly, you do not have any scale, and that's only...
But when at weak coupling you had this picture, still a cut, but no bound states.
Very good. So let's discuss the connection. Now, you can ask. Here you see there are two things happening. One is the rotating strings. This is this thing. And this was related to the potential. So this business of rotating strings is this. This bound state, this ground state, it corresponds to the leading radial trajectory, and it always exists. So this leading trajectory just follows the bound state. But then you can ask, okay, what about these guys? So these guys should correspond to subleading radial trajectories. And already here, it seems like, in principle, we have everything to understand that, but this has not been understood. So subleading radial trajectories. In particular, what you would like to do, you would like to take a subleading radial trajectory and check that it does not produce any bound states, for example. This would be at weak coupling. And at strong coupling, it will. And the picture is, of course, that if you take a rotating string at strong coupling, it's just Veneziano. So surely it has infinitely modes, which is just excitation of a string. But at weak coupling, it's not clear. And there is a conjecture by, again, Simon and Johannes, of the relationship of the subleading radial trajectory to the gamma cusp with an insertion of extra scalar field, but it has not been computed using integrability yet. But in principle, it should be possible, and then one should be able to check.
What's the conjecture again?
The conjecture is G1 plus 1 is equal to minus gamma cusp with the insertion of a phi at the cusp. So you insert a scalar field at the cusp. Basically, you have a gamma cusp with this phi, and you start inserting some defects there, and they have a strong evidence for this conjecture, well, based on loops, some explicit computations. And intuitively, it seems like this subleading radial trajectory should capture this quantum number n, but this has not been understood. So, and again, the intuition of Maldacen and Raman seems, for them, it's obvious that this is what should happen. That this guy should be there, and so then it seems like that if you take Jn of t, the subleading radial trajectory, perhaps when we take this n to be very large, we will have some accumulation point, and maybe there will be extra accumulation related to this guy. But the physics is different. So here there are dynamical quarks which are rotating. Here it was a static Wilson line, but somehow the pictures, the two are related. But I think it would be very interesting to take G1 of t, and show using integrabilities that there are no ground states at weak coupling, and there is a transition. What is the coupling of this transition? What does it appear?
What do you mean, no ground states? I mean, this
Sorry, no bound states. You try to solve this equation for integer t, and you will not find solutions for real. Okay, that's the Um,
A very weak coupling.
Yeah.
So this has been done by Johannes and Karamot.
Yeah, at weak coupling, you do it up to 3 loops.
Mm-hmm.
You can do it at 3 loops, and I believe we checked that there are you do not get bound states here. For example, you get to leading order. It's really, you see it already the first order. You do this first order computation, you see immediately the bound states, and you do for J1, you don't have them. Effectively, J1 of T has an expansion which is something like -1 minus a constant, and it never has a solution. But it has to be done at finite coupling. Yeah. And okay, so the question is that I want to move next is how are we? So the basic moral here is, I guess, that there is this object which has many interesting properties. It interpolates between one loop box and Veneziano. It has accumulation point. It's unitary. Blah blah blah. And we have an extra handle. In principle, we have an extra handle because of supersymmetry. So there is a super amplitude. So there is a SUSY, which is a kind of trivial, but it has some interesting consequences. And the second is that we know, or at least we can hope to know, Regge trajectories from integrability. And now the question would be, okay, maybe we need to find a principle how to solve this theory. Well, just to say right away, I don't know the answer, but we would like to find the principle how we can try to hope this, to fix this theory. And okay, one natural guess would be that we want to use combine this with S matrix bootstrap.
So Regge trajectories, because you can take this M to 0 limit and they somehow stay the same Regge trajectories, you can take conformal Regge trajectories, whatever, in the plot of delta, in a delta J plot. These are the Regge trajectories that are known from integrability, right?
So you know gamma cusp from integrability.
Okay, and then you use
and
this.
then you use it. Yeah. So it's not closed string. So there is a whole separate story about closed string flux tube, which again, a lot of integrability, a lot of work. Here it's a kind of open string version of this. And you know from integrability gamma cusp. And then you just use gamma cusps and various variation of thereof to compute the Regge trajectories using dual conformal invariance and this relation. It's known for the leading Regge trajectory, but there is a proposal for subleading one, and I think there is. It seems like there might be story.
But is it integrable, the cusp with?
I don't know. I think okay, maybe someone knows, but I thought Kolya was writing papers on that.
So for subleading, you say you just need to have this gamma cusp with some insertion. That's the conjecture.
Yes, that's a conjecture.
In this formula T form squared over sine squared phi, that's something exact. That
Yeah,
was
exact.
like Gabriel
That's
was
exact. That's
explaining that some geometric
Yes.
thing. You know how to get the Regge trajectory in the Higgs phase from a conformal phase, assuming this dual conformal invariance.
Yes.
That's the trick.
That's the idea. And so then we would like to try to at least maybe. The question is, what is the principle? Can we now formulate a principle? I mean, if you can solve strings and ideas, okay, then you don't have to do anything. But the question, which I think is interesting, what is the principle that might fix such amplitudes? And I think this principle has not been found yet, but there has been, again, many works on that. They do not talk about this problem, but effectively they are kind of doing the same thing. And so I want to comment on that. So basically what we want to do is the vanilla sort of S matrix bootstrap in the sense that it's just positivity. It's a planar amplitude. So we do analyticity, crossing, and unitarity. And I guess Jan will explain in detail next week what this means and how to do that, because there is an interesting work on the same thing with Confining. defining strings. And here we want to combine it with integrability, which potentially means to the same as the leading radial trajectory. That's the idea. Maybe then you can hope that if we can define this theory as a theory that maximizes something, given this set of constraints plus the input from integrability. And presumably, if one does it properly, it should work. But one needs to find the right ways. I can tell you some exploration now of this idea. And in fact, we can ask even a simpler question, because you see that, as I explained, that this amplitude, it has as its limit Veneziano amplitude in flat space. And therefore you can ask, can we fix Veneziano amplitude by some principle in S-matrix bootstrap? That would be the idea, and that's what people have been exploring. And so let me first comment on the in fact, there was a paper, well, there is a series of papers by Yuting Huang. And there were two papers, last of them last year, also by Henriette Elvan, Berman, and Hardashe. So let me write it like this. Now, 23, where they ask exactly this question. They say, well, let's consider a supersymmetric amplitude, which is meromorphic. Well, effectively, they were thinking about this guy. And we try to understand if we can fix it somehow. And what they say is that, well, let's take a simpler case where the amplitude is really meromorphic, so it's a strong coupling scattering. And they say, well, from the world sheet we know, if we take the explicit strings, that the amplitude satisfies what's known as the monodromy relation. So if you consider ordered scattering, just using the world sheet integral, you can show and check that the amplitude satisfies this. But I also recommend you can take this paper by Henriette Elvan and friends. And what they say in these papers is that, well, what if we combine S-matrix bootstrap plus monodromy relations? And how can you combine it? Well, you just take this formula and you expand it at low energies. At low energies, each of these guys is a bunch of Wilson coefficients. So this relation leads you to infinitely many more relationships between Wilson coefficients than you can put in. And the conclusion of this paper is that, yes, Veneziano is picked by this monodromy relation. So if you take a bootstrap bound, you put this in, Veneziano emerges as a point. However, you can ask, okay, well, it seems like it does not really help us maybe directly, because if I take a one-loop box, which is in the same universality class, of course it does not, it violates this monodromy relation, so conceptually then the question is, if this selects Veneziano, super Veneziano, then morally the question is, what is a generalization of monodromy relations to finite lambda? Or something like that. So we want equation something like that, we solve it, and maybe we fix it uniquely. And here, effectively, this is a leading radial trajectory. So maybe it makes sense that we should put some leading radial trajectory in. But otherwise, we don't know because we do not have a bullshit theory. A second series of paper which I would like to mention, which has been happening these days on arXiv, is by Aldai and collaborators. And what they did is that they say that basically you can compute you can fix 1 over square root lambda corrections. The first one uniquely, and here there is some freedom. By using what they call single-valuedness, the principle of single-valuedness, where they kind of start mimicking the world sheet in ADS by imagining that the first order leading correction is some kind of insertion of a closed string vertex operator on the world sheet, and then by assuming some the properties of such integrals and then imposing crossing and everything, they manage to fix the first correction, and I think they're almost the second one. But again, I think this is something which only makes sense perturbatively in lambda, because it seems like at finite lambdas there is this cut, and but okay, this just to say that this works from the last year. From this year, they go a little bit into the direction of trying to fix this amplitude by using some properties of the world sheet. Okay, that seems interesting, but I don't know how to do it. I think no one knows how to do it at finite lambda. And to make some progress, what I'll try to do is I'll follow this, which is that, well, this we know how to do at finite lambda. Because leading Regge trajectory is defined at finite lambda. So maybe we can just go and try to play this game. This is what I would like to say a few words next. How do we... Here I said that monodromy relations fix the amplitude, but now I don't have monodromy relations. I want to find another principle or explore another principle which maybe tell us what the theory is. Yeah.
Is monodromy relations, is that somehow assuming you're in flat space? Or?
Effectively, yes. It's just a flat space world sheet integral. You just take a flat space string, z minus 1 minus z, and then it's very flat space, I'd say. Yeah.
What is J0 of 0? Strong and weak coupling?
It's always minus 1, I think, because it's just a gluon. But then I think it's weak coupling. Yeah, strong coupling, it's linear, of course. It's kind of square root lambda t. At weak coupling, I should know that. I want to say linear, but somehow I'm not sure. So, but surely we can compute it. I would expect it will be linear because there is no reason to set the linear coefficient to 0. So you'll just get 1 plus lambda t, or 1, or it's strong coupling and get square root lambda. But it starts always at the gluon point. Yeah, by the way, so there is a supersymmetry. I said there is, for example, one famous result about this amplitude. So there is a non-renormalization theorem for the 4-point low energy, like the first leading Wilson coefficients, and it was even used in the original paper on ADS-CFT by Juan. He considered DBI action, and he computed the 4-point amplitude of dilatons and matched it to weak coupling, and this was one of the ways to see that ADS-CFT makes sense because supersymmetry predicts it's normalized. So this is all part of this. It's the same object. In a proper kinematics, in a proper member of supermultiplet, you have a scattering of dilatons. Okay. When shall I finish?
20 minutes.
Okay. So I will use 20 minutes to say about what we've been doing with this game. Effectively, we'll be just listing the results. So let's do this matrix. Bootstrap plus leading Regge trajectory. And the first thing we can ask, imagine the simplest possible setting where the leading Regge trajectory is just linear. Let me be first sloppy about the intercept, which is in principle important, but let's just take it's exactly linear. So what does it mean? Well, at positive t, it tells you that here it tells you that the spectrum of resonances 1, 1, 2, 2. And at negative t, it tells you that the amplitude becomes very soft. What I mean by that is that if you take the amplitude to be s to the j of t, you see that when j of t becomes negative, this is become more and more negative, it decays faster and faster. And intuitively, so it's very soft. Intuitively, this is already a signal of a very fine-tuned system. Why is that? It's because if you write dispersion relations, you can effectively use these guys, this condition. You just take a contour at infinity, some ds s to the n a, and if t is negative enough, this contour integral gives you 0 because a decays fast. On the other hand, you deform the contour and you pick the residues here, and you get the equations of this type: 0 to infinity ds a s to the n equal to 0 for j of t less than -1. In other words, this imaginary part is a sum of Legendre polynomials with some positive coefficients. All Legendre polynomials are oscillating, but they are perfectly tuned in such a way that these sum rules are satisfied. And so let me call this Regge sum rules. And effectively, the connection is that if your theory is not tuned, for example, if you have like large n QCD, you do not expect this to hold. And I think this is related to the fact that in QCD, the Regge trajectory for positive t is this, but for negative t it bends, which reflects on the sense. From this point of view, it reflects on the fact that the imaginary part is not tuned. It's not less tuned. It's not satisfied. And therefore, we can now take a matrix bootstrap, and we can try to impose these two things. First, we can impose this leading Regge trajectory for positive t, and this is as clear from here. It boils down to saying that there is a maximum spin in the spectrum. In other words, let's say you take imaginary part at some value of t. It's a set of resonances. A priori, if you're just a matrix bootstrap person, the spin can be whatever you want. But the leading Regge trajectory tells you that it's bounded by the leading Regge trajectory. So this is something very easy to implement in the current scheme of deriving bounds and Wilson coefficients.
The maximum spin of the spectrum for given s.
For given s. No, now for any s, right? Because you know this for any t. So you can impose it for all t. You have a maximum spin. And for example, this immediately kills an amplitude with accumulation point at finite t, right? Because it tells you that you cannot have infinitely many particles at this point. That's first thing you can try to do, and okay, we've done that, and it does reduce the bounds, and we get some plots, but it's clearly not enough. It's not strong enough as of yet. And the second thing you can try to implement is you can try to put this Regge sum. In other words, you have a condition, in principle, infinite set of conditions that these guys have to be 0. It's a condition on the imaginary part. However, what happens here is that the imaginary part is a sum of Legendre polynomials, and because t is negative, they're oscillating. You just try to add this sort of null constraints into the bootstrap solver, it sets them to 0. So let me let me say it like this. In the technical language, it will say in the dual, no effect. However, in practice, this is not yet conclusive, maybe fully, because in the way you do it technically, you have infinitely many sum rules, but in practice you can only implement finitely many. So you could be still say, okay, maybe I'm not convinced by the current technology of the dual bootstrap. Let me try to just see explicitly if I can construct many amplitudes which satisfy this system. So basically, the idea would be that maybe what is important, and I guess several people thought about that, what selects string theory is the softness compared to other strings, the fact that it can go arbitrarily far. And again, as I said, that in this dual way of just deriving bounds and Wilson coefficients, you cannot do it. So, but what you can do is that you can play a primal game. And that's what do I mean by that? What I mean by that is that you can explicitly write an ansatz for the amplitude, which satisfies all the properties you want. And if you assume, as we have here at strong coupling, for this string at strong coupling, the spectrum is just equidistant, you can argue with some level of convincingness that the complete ansatz that you can write for this Regge trajectory is given by this formula. So what is put in here? First, spectrum is equidistant, the position of the poles is integer. The Regge trajectory you can check with this choice of these guys is linear. Third, you can check that all these amplitudes satisfy the Regge sum rules. So the question then becomes, the only thing that you have to check is unitarity. And let me present some results, what happens if you do that, why the problem is tricky. First, if you, and again, so here, again, what I'm doing S-matrix bootstrap with the leading trajectory being linear. That's all I'm doing. And I'm trying to see if from all these guys, Veneziano is the only solution. First, you can very easily prove that if you truncate this sum to any finite number of terms, then the only solution is Veneziano. And to me, it's a little bit similar to this monodromy statement, because if you write this integral, which is truncated sum on the wall sheet, it's effectively like taking a usual stringy integral and inserting a polynomial there, which of course does not introduce any new monodromy. So it makes sense that if you impose, it seems very similar to that. Well, okay, the only solution is Veneziano, but it doesn't tell us yet that first you cannot go to infinite solutions. But it makes the problem hard, and I think it's an open problem. Say in the usual S-matrix bootstrap, and in fact, if you do the same thing for closed string, even for finite and max, it is unitary. And in the usual S-matrix bootstrap, a la Andrea and friends, you can do it at finite and max. But for open strings, it's open. We don't know how to do effectively this primal bootstrap because these guys because all these guys violate unitarity, but, which is suggestive from this point of view that it's good that they violate unitarity. Maybe we can fix the amplitude to be.
There are these solutions, this hypergeometric with some f2, 3.
So yes, if you look at there are papers of Chong and Remen. So papers by Chong and Remen, they of the same type. So they also of this type, this ansatz. And they satisfy this, but they violate that. The residual limit looks like this. That's why Chong-Remen, satisfy that, not that. However, you can write an amplitude. Yes, that's in fact people tried in the past. Mandelstam had a paper on that. There is also this guy Matsuda who wrote a paper, and sometimes these shifted gamma functions are called satellite terms. And the way you can consider the following deformation of Veneziano. And here you introduce first you immediately see that it goes beyond this monodromy relations, because effectively you introduce a pair of complex conjugate points, which are a little bit in the spirit if you consider closed string scattering. If you send the graviton on a D-brane, it's like insertion of a closed string vertex operator on the wall sheet, but here we do not integrate over it, but we have an extra branch point somewhere in the complex plane. From the point of view of this amplitude, everything is analytic, and you can check that these amplitudes, they satisfy the Regge limit, they satisfy everything, and then you can find a finite region in the parameter space C0, C1, and lambda, such that unitarity is satisfied. This is just to say that clearly at this level, this disproves that you can have RSR without it being Veneziano. So RSR is not this Regge sum rules are not enough. But in fact, just from doing this exercise, we already learned something interesting. And there are several things. I will just again list it as a comment because first you can take the high energy fixed angle limit of this amplitude, and you will find that they have a form of Veneziano plus extra in general. This contradicts the paper we wrote with Amit, Simon, and Zohar, and for good reason is that we made an assumption in that paper which is not correct. So there was a technical assumption about the support of Legendre polynomials, which we used to fix it, and you can just explicitly construct the amplitudes which are unitary, and you can just see that they have the extra term. So in fact, if you think about it then, I think a better version of the statement that we had in the paper is not this, but this. And this you can derive with some better rigor than what we had. So this is already something interesting, which tells us that if you will just do bootstrap with analyticity crossing and unitarity, and you try to reproduce our results with from whatever, you will not be able to do it because there are other solutions which are different.
Sasha, what is the Regge behavior of the extra term?
This?
Yeah.
The Regge trajectory is the same. The Regge trajectory is not modified. What is modified is a fixed angle. So you take S and T both to be large but fixed, and you have a formula which is different from Veneziano. But if you go back to the Regge limit, you just recover JFT. In fact, there is even more obscure things that are happening, which are interesting, but okay, I don't have time to discuss that. So that's one lesson you can perhaps learn from that. And yes, just to say again, in that old paper we consider the sums of Legendre polynomials with positive coefficients, and we said that if it's a positive sum and if it reproduces the radial limit, then the support of zeros of the sum should be between -1 and 0. But these amplitudes show you that you can have a radial limit and positivity and have support arbitrarily far in the complex plane, all the way to infinity. This assumption was too restrictive, and it goes beyond the bootstrap. So either we justify this assumption or we add it or whatever. The second point I want to make is that, which is a bit interesting, is the following. So, in fact, this guy, this integral, if you set here I and k being 0, it becomes gamma minus s, gamma minus t, gamma minus s minus t. Now, if you look at the super Veneziano, which relevant for this first part of my talk, it looks like this: gamma minus s, gamma minus t, gamma minus s minus t. And effectively, it boils down to the fact that what happens for this, what supersymmetry gives you, as it often does, is that one should consider the same problem with jt equal t minus 1. It lowers the radial intercept. So, super Veneziano, and you can check that if you try to take all our amplitudes and you try to apply them to deform a super Veneziano, it doesn't work. They all violate unitarity. So in principle, it's one possibility which is open, is that RSR plus SUSY equals to what? We don't know. Could be that, I'm sure there was no systematic derivation of the ansatz, so the most natural guess is that, well, we still get a bunch of stuff, but just a curious fact, we were not able to construct such solutions. Next point, which you could ask, is the following. What happens? So, for example, if you show this amplitude to David Gross, he says, I don't care, I need a 5-point amplitude. Because in the 60s, we learned that 4-point amplitudes do not teach us anything. Everything comes from factorization of higher point amplitudes. And in fact, there is a really nice paper by Gross from 65 or something, where he took this amplitude with satellite terms and he promotes it to the Sn, the n-point amplitude, which satisfies factorization. So there was a paper, for example, by Nima and friends, that if you take some of these deformed amplitudes, they do not satisfy factorization. Here, you can just take this amplitude and you can write an ansatz for n points, which does. It's really simple. And it was done by Gross in 65. But the kind of lesson from these studies in the 60s was the following. Well, after you have an ansatz, and basically the ansatz goes like this. This is your Walsh-Schmidt integral, and then you write the n-point amplitude in terms of the Walsh-Schmidt integral, and you just consistently write this integral, which gives you factorization. In fact, and there is also a big ambiguity in this procedure, as he showed. But what people then started studying, well, if you have an n-point amplitude, you can start studying two things: unitarity, and you can also discuss the thermodynamic properties, the growth of the density of states of such amplitudes. First, well, unitarity no one has checked, so in principle you can check it, and with the simplest deformation of the Gross type for the higher point amplitudes, we can rule out all these guys except Veneziano. But it's highly ambiguous because you can start adding kind of 5-6 point amplitudes, so it's not complete. But for the simplest, most natural thing, okay, you can rule this out. But another moral, which the game that people play, is that if you want your theory to be consistent, you can take your amplitude, sit on some pole, and the number of flags here is arbitrary. And if you fix this mass, if your theory is consistent, it should admit the Hilbert space interpretation, so the number of states here should be finite. No matter what you take for the external guys. It's always a set of states. And what happens is that for the 2 to 2 point amplitude, you have a set of string resonances, but they're highly degenerate. So you do not see the Hagedorn growth of states. And how people in the 60s discovered the Hagedorn growth of states, you write the amplitudes, you make sure that they factorize properly, you read off the density of states, and you get that it's Hagedorn. So what people found in the 60s is that if you try to include any satellite terms, you always get super Hagedorn growth. So it's not a theorem, but that's why people stopped playing these games, because you write something natural and it just grows crazily fast, so it doesn't have a nice... Yeah.
How did you extract the density from this object?
Yeah, so what happens is that, let's say you have any number of point amplitudes ansatz. You take the residue, and your residue should always be written I to the n as a Ci, a left, a right, independently of the number of the guys here or there. And what they found is that, in principle, all these guys also could be, I guess, degenerate, but what they found is the minimum number here. And so you see that you can factorize, but you start resolving the degeneracy. And then they see that, in fact, satellite terms, they violate Hagedorn growth, which is kind of an interesting thing that it seems, if we put in the S matrix bootstrap the thermodynamics in the terms of Hagedorn growth, it seems like it's a very powerful constraint here, of course. And the second comment is also, if you impose, you can now try to impose unitarity of the massive guys again with some ansatz, and it was done for the, I guess, this Lovelace-Shapiro model for the pion scattering by De Vecchia and collaborators a few years ago, and for the pions they showed that the first massive state violate unitarity, and here we find a similar thing. So we can rule out, we guess, for certain deformations. So in principle, I could probably show you some plots on the bounds, how you can now impose analytic crossing unitarity, supersymmetry, maximal spin. It reduces the shape, and Veneziano lives not far from the boundary, but it clearly is not fixed. And it seems like there are a set of open questions, but hopefully with some input from integrability and a proper bootstrap strategy, when we understand this monodromy relations at finite lambda or something like this flux tube, which it seems like the simplest flux tube, should be solvable. So that's the basic picture.
Sasha, I lost connection between the first part of your talk and the second. Yeah. In the first part, you explained to us this amplitudes with accumulation point and whatever continuum part, and then you said that in n equals 4 you can set up something very similar, and then you said it's an interesting question how this interpolates between weak and strong coupling. But then you switch to studying some very different amplitudes that have this linear thing, do not have accumulation point, do not have this logarithmic tail at low. So
the idea is that if you take the strong coupling limit, it looks like Veneziano plus corrections. All these features of accumulation points, etc., they push to the UV. For the bootstrap games, you can ignore them. So to me, I took a stance that, okay, let me try to find a principle to fix this guy. And then my hope is that, imagine I play this game, SUSY plus RSI plus leading register rejected and it's fixed, then I use integrability to go to final number, and maybe it works. But they were maybe loosely connected.
Then it's very strong. But you say you rescale. You look at that picture.
And you rescale.
And that's what you're trying to understand.
Exactly. So it just, basically what happens that there is a weak coupling eye. The weak coupling eye looks at the problem like this. There is a cut at two particles, which is obvious, and there is a bounce state, which is not obvious. And there is which is very close to the origin. This comes from this dynamics of this bounce state on the string. And there is a strong coupling I, where, this is just the string modes, 0, 1, 2, but the cut is very far. And they just related by rescaling. But
then I thought at some point you said that these bound states are subleading Regge trajectories.
Yes.
But
in the flat space,
this thing has subleading Regge
trajectories. Yeah, it has all of them. All subleading Regge trajectories. But close to the origin, in a sense, we zoomed out.
I see. So you have a bunch of those, but
you have
not
infinitely many going down, and we focus here.
That's I understand.
That's basically what the idea is that Veneziano is just the leading term at strong coupling, and therefore all this work could be directly sort of thought of as a leading term approximation to M4 last year.
No more questions. We'll just